It is a couple. It is a couple of minutes before the hour, so is it okay to go ahead and get going?
Yeah, we could get started.
Okay, so I'm really glad to be here and to see what a bunch of bright-looking, awake people. I wanted to mention some resources before getting into the material. So this material I'll be talking about today is from the course notes from my regression modeling strategies course, which is a full semester course I'm currently teaching at Vanderbilt University. There's also a 4-day sort of cram version of the course that we offer virtually every mid-May. But there's a central website for materials that you may find useful, which is hbiostat.org/RMS. That will get you to the course notes and also information about the book and a lot of other resources. There is another resource. Oh, and here's a direct link down here to the course notes that you're seeing on your screen now. There's a couple of other resources that you should know about. One is datamethods.org. This is a discussion board that was created to be a place where methodologists like statisticians and econometricians and epidemiologists meet subject matter experts. So when subject matter experts have a question that involves methodology, or a methodologist has a question that a subject matter expert can shed light on, that's really ideal. They're really health related, mainly questions. They can be more general, but more health related. Plus, we have a lot of debates, including some extremely long debates, because when you get into what is a p-value and what is a confidence interval, you actually open up endless debates about what those things really mean, which is what drives a lot of people like myself to Bayesian statistics rather than frequentist statistics. So I would encourage you to look at that resource, and there's a special navigation page with this address that will navigate you to different sections related to regression modeling strategies. And then there is the world's most popular statistics and machine learning question and answer site, stats.stackexchange.com. This is really for general statistics and machine learning and prediction and validation. And it's not related to any one field like health or economics or sociology. It's very general, but it is the most active site in the world for those kinds of questions. And it's related to another site, which is called stackoverflow.com, which is the world's busiest site for questions about computer programming and various computer languages. So that stackoverflow.com is the place to ask questions about the R language and certain other programming and statistical languages. So take a look at that material and those resources. And here's another resource. I have this course called Biostatistics for Biomedical Research, and that is a general statistics course that's about 500 pages of notes and a lot of videos and a lot of podcasts. And the examples in here are almost all medical, but the methods that are being presented here are very general. So this is sort of a course that may precede the regression modeling strategies course and cover everything I know about statistics other than Bayesian methods and other than regression modeling strategies. But like if you wanted to learn about non-parametric statistics, that would be here. And then if you wanted to learn why you don't need any non-parametric tests, that would also be here. And the reason I said the latter is that non-parametric tests are special cases of regression models. And regression models are going to be a better way to do non-parametric tests because you can handle multiple variables. Whereas a standard non-parametric test like the Wilcoxon test for comparing two groups, you can't adjust for another variable while you're doing that. So I like to think in general, what is the general way to present things? So semi-parametric models are also called ordinal models, are covered in this course as a substitute for things like the Wilcoxon test. There's also my blog, fharrell.com, that has a lot of articles that are related to what we're going to be talking about today. So what I'm going to cover are some pieces of the regression modeling book and course really to get your appetite whetted, um, and to show you what some of the things, uh, some problems that we have in statistical analysis that are not usually taught. And so I like to cover things that are often omitted from other courses, because I think they're important and because they're also sometimes actually fun. So the first thing that I'm going to talk about is specifying a model in terms of, say, a single predictor. So let's say you're predicting somebody's wealth as a function of their age. So X1 here would be age. And C is just a general notation that I use in the course to represent a property of the response. So this is just to point out that when you're doing a statistical model, most people start by estimating the mean, but you don't really have to start there. You can do quantile regression and estimate a quantile, which is fairly popular in econometrics. You could be estimating a standard deviation, or you could be estimating a hazard rate. This can be anything. When we get into a binary logistic regression example, what this is the probability of an event given the predictor variables. Now, what you call the predictor variables, they're often called covariates or independent variables. I just have kind of settled on the term predictor, even in cases when we're not actually interested in prediction. So the thing that you first see in most courses is you would stop right here and you would be introduced to the linear model. And this, instead of C, might be capital E, which would stand for expected value or long-term average. So just think of this more general than the mean. But then if you said, well, this accumulation of wealth, is it going to be linear in age? You would have a model like this if you were interested in modeling, say, the central tendency of wealth. And you would have a very, very unrealistic model. And just speaking in general, one of the biggest mistakes people make in statistical models and analyzing data is the assumption of linearity. So when you think about how nature works, there's really very few things in nature that act linearly. We have Newton's laws of motion, that if the velocity is constant, the distance you move is going to be linear in time. But that's one of the very, very few equations that we have where you really expect things to be linear. And so we need to allow things to be nonlinear. So linearity is kind of an accident. Um, so when you're predicting one variable from another type of variable, we just very seldom want to assume linearity. But I noticed that in economics, these linearity assumptions are made fairly often, and I think it's a very harmful type of assumption that matters a lot. And so how do we allow it to not be linear? Well, this is the first thing we're shown, is to add a quadratic term. So now you've got a parabolic relationship between age and wealth. And it's a quadratic equation that has a vertex and it's symmetric on either side of the vertex. So that is a lot better than just assuming it's linear. So you may allow it to be kind of a shallow relationship that kind of takes off. And a quadratic can capture a good deal of that. But there are just not a lot of things that actually act in a quadratic way. So quadratic is going to be symmetric around the vertex, and it's not going to allow anything that looks like a logarithmic relationship, and it's not going to allow a relationship that turns more than once. So we need something more accurate than that, because if you make predictions from a quadratic equation, your predictions are not going to necessarily be very accurate. So you've got lack of fit. So we can get more flexible by adding powers higher than 2. But when you start using polynomials in general, they don't really work well enough. So if you have a logarithmic relationship, you have kind of a rapid rise and then it sort of tails off for a long time. You can't really fit that sort of relationship with a regular polynomial. And then when you fit a polynomial, you'll get peaks and valleys in your fit that no one can understand because they're not real. And so we need a very general purpose way to deal with nonlinearity. And one of the most popular is a spline function. So there are physical splines that are used to draw curves that are smooth. such as bending a piece of metal and taking your pencil and drawing along that to get a curve. And then there's a spline function, which is a piecewise polynomial. So what we're going to do is, instead of having something like this, we're going to have something like this that's pieced together with other polynomials at a join point. And the point at which they join is going to be called a knot, K-N-O-T. And that's what allows us to be very flexible, and it tends to just work well in practice. So there aren't many relationships that you find in practice where the spline function is not satisfactory. The one place where a spline function, the way we usually fit them, is not going to be satisfactory is if the variable here is time, and you're looking at something like a stock price here. So Y is a stock price, X is time, and then the CEO of the company is indicted for fraud, and the stock price takes an immediate dive. So when X is time, you can have events happen, and events cause instantaneous change. So you can have a relationship that goes down and it takes a very rapid dive that you wouldn't fit well with a regular spline without being very careful about the join points. In a lot of situations, we don't have time as the variable, and we don't have events happening that create discontinuities. And so the spline functions tend to be very smooth. Now, if you start with a linear spline, they're not smooth, but they can still fit very well, but they lead us to what we need. So bilinear regression is something that's been around a long time. You have a linear regression if you're to the left of A, and you have a different linear regression than if you're greater than A. But if you fit it like that, when you plot your predicted values, you'll have a straight line here and another straight line, but these two will not meet vertically. So you have a zero order discontinuity in your fit, because you see these two lines are not connected to each other. So we need a way to put a restriction so that when you're fitting two lines, they're going to meet at this join point. So what we want here is not a sudden change in the intercept, but we just want a sudden change in the slope on that second piece. So we can force that simple continuity by putting a notation like this. So we start with the initial line that has a slope of beta 1, and then we have a term that's ignored if X is less than A, and it's not ignored if X is greater than A. It's also ignored if X is equal to A. So by fitting this equation, what beta 2 becomes is a change in slope. So it's, instead of being the new slope on the second line like beta 3, this is a change in slope from the original line going from left to right. And as you go from the right towards A and you go from the left towards A, they will both meet at the same point as X approaches A. So this is the notation that we use to make that happen. This is with 3 changes in slope. So this is a linear spline function with 3 knots. So we have an initial slope, we have a first slope increment, a second slope increment, and a third slope increment. And these terms are ignored if they're negative. That's what the plus means. So only use this term if it's positive. Likewise for this and this. So this will make sure that you get a graph that looks like this. It's 3 slope changes at X equal to A, B, and C. And you're not going to have a zero order discontinuity at any of these knots. So this is going to allow you to fit a lot of things very flexibly, but the downside of this is it's fairly sensitive to where you put A, B, and C. And we don't see these sort of things in nature. So in nature, not only do we not see a zero order discontinuity where there's just a vertical jump, we don't see discontinuities in the first derivative or the slope of the function. So we don't see elbows in nature unless this is time, or unless a law kicks in. So, we have a law for the voting age and for the age you can smoke cigarettes and age you can serve in the military. So if you plotted age here versus certain things, you can have complex relationships that are discontinuous or have elbows in them. But other than legal mandates, you don't really see that sort of relationship. So I hope you're starting to see how this notation works, because we're going to use the similar notation uh, to do curve fitting in general, where instead of just changing the slope, we're going to change the shape of the curve. And we're going to have smooth transitions instead of elbows. So this is a building block. And just to take a step back to talk about why this is so important is if you don't pay attention to fitting the variables correctly and flexibly, you're going to have lack of fit. Your predictions will not be accurate, and you'll find your model may not be adequate, and you need to go and measure something new to make the model predict well enough. So if you don't use something old effectively, all of a sudden you'll need a new variable to be added to the model to make up for the lack of fit. And we don't want to have to go and measure things just to make up for us modeling something poorly by assuming it's a straight line or assuming it's a quadratic when it's not. So the idea of getting the most out of every variable is a key idea in regression and in research in general. And another place this shows its head is we see a lot of papers where people compare machine learning to regression. And if it's a machine learning expert that ran the simulation, they usually report that machine learning does better than regression. And then if you look at how they did the regression, they forced all the x's to be linear. So they're using regression and how regression existed in 1960, and they haven't used any advances in regression since 1960. Seems a bit unfair. And then when you allow this to be flexible, all of a sudden you see the regression model being extremely competitive with machine learning or even better. So this idea of getting adequate fits is extremely important. Also, it gives you better interpretation. So that all leads up to what we really use as our default fitting function for handling a single predictor, which is a cubic spline function. And so a cubic spline function, it starts off with that linear part, and now you've got a quadratic and a cubic, and now you've got shape changes. These are, instead of calling these shape changes, you'll see in a moment, these are really changes in the third derivative, to be specific. But what you're doing is adding what's a slight shape changes, and you're changing the shape every time you cross a knot. So we have changes at the point x equal to a, b, and c. We'll put all that together and just abbreviate the model as x beta. That's called the linear predictor. And that's just going to be the combination of all of these terms. That's just a shorthand using a matrix notation or vector notation. So now you see that when you're fitting that model, you'll be able to fit it very flexibly by putting these variables in your model. So this variable is, in programming notation, would be the max of x minus a and 0. What's the maximum of those two numbers? Max of x minus a and 0 to the third power. So that will give you x4. And you do likewise for the others. So this is going to be a very flexible way to fit things. It has a linear model as a special case. It has a quadratic as a special case. And then the way that you kind of build up the understanding of this, this is an example function. This is a cubic spline function that has change points at x equals 0.25, 0.5, and 0.75. And so here's the whole equation, and x goes from 0 to 1. And you see where the knots are there. So if you just evaluated that and evaluated its derivatives, you see the graph here. So what we're doing by fitting this kind of function is we're actually creating thresholds for the third derivative. So you could say that we're categorizing the third derivative of the function, which is a far cry from categorizing the original variable, which is going to be inefficient. So we're going to have a piecewise flat third derivative. Third derivative in physics is called the jolt or the jerk. So that's the rate of change of acceleration. So we're making this be discontinuous. It's the only thing we're having discontinuous in our model. So if you look at the second derivative, which is the acceleration of your function, that's the rate of change of the slope. It's going to be a linear spline. So it's piecewise linear. And then the slope of our function is going to be this piecewise quadratic function. It's the rate of change of the original function. And this is the original function. So you can see this is a very flexible kind of curve. And the knots happen to be here at these three numbers. And then you see the slope of that curve, the slope of the slope, and the slope of the slope of the slope, or the jolt. And so we are allowing the jolt to change instantaneously. But the nice thing about having multiple levels of continuity, because it's a cubic function to start with, is if you look where these change points are, the human eye cannot see. So if those vertical lines were not there, you would not be able to pick where the changes in the third derivative were. So the bottom line there is you're piecing together a very smooth curve that's going to meet almost any of your needs. And it's going to be very smooth, and you're not going to be able to identify any sort of elbow or discontinuity or anything like that. So having a discontinuous third derivative, the human eye can't see that at all. So that's our basis for modeling as our best default sort of nonlinear relationship. And then the way to go forward from there is when you look at this function, if you fit it in general, you sometimes see some curls in the extremes, and you see a little bit of noise out here. And it also takes a lot of parameters. So we started with one variable, and you see if you were estimating this equation from data, you have to estimate this coefficient, which happened to be 1. In our example, you'd have to estimate this coefficient, this, and all these others. So you have a lot of coefficients to estimate going back to our original equation here. So that is 6 regression coefficients plus the intercept. And that's just for one predictor, and we might have 20 predictors in the model. So it's sort of getting out of hand. So our next step we take is to use what's called a natural spline or a restricted cubic spline. And we're going to force the model to be linear on the left. So when x is less than a, we're going to make this function of the predictor be linear. So we're going to force beta 2 and beta 3 to be 0. And then we're going to make it be linear on the right. So to make this linear on the right is not as clear, but you're essentially getting rid of beta 5 and beta 6. And actually, you're not getting rid of those explicitly, but you're getting rid of 2 out of the 3 degrees of freedom. And so you're going to end up having one regression coefficient to solve for this part of the model. And the coefficient that what it multiplies is a bunch of terms involving all 3 of these, which you'll see in just a minute. So that's kind of a nightmare, but that's where we're so glad to have software, because the software does this behind the scenes without you having to combine terms or deal with any sort of algebra. So what that ends up looking like, which is kind of the bottom line, is when you create these derived terms and you put those in your regression instead of the original terms, this will make the linear restriction apply to the right part of the equation. So the right part is going to be when x is greater than the last join point, t sub k. These derived terms will all be linear when you're in the right tail. And then we've gotten rid of the square and cube terms, so it's going to be linear in the left tail. So what does this actually look like? Well, if you had 5 knots that were put at 0.05, 0.275, 0.5, 0.725, and 0.95, having 5 knots and having linearity at the tails means you have 3 nonlinear functions to include in your regression, and you have 1 linear function. So this is the beta 1x1 part. So if you have 5 knots and you have linear tails, you're going to have a grand total of 4 degrees of freedom. Before we would have had 8 degrees of freedom without the linear tail restriction. Now, I don't know if you've heard of basis functions, but basis functions are the bases for curve fitting when the curve fitting involves linear combinations. So in the quadratic equation, the basis functions are x and x squared. So you have 2 basis functions, and your job is to find their coefficients. The coefficient of age and the coefficient of age squared, when put together, will give you a quadratic fit. Likewise, when you solve for 4 coefficients for these basis functions, you get a restricted cubic spline fit. So for example, let's say what you see in your data is you have a relationship that starts off going up. Okay, this will have a positive coefficient. And then if the relationship turns downward, you'll have a strong negative coefficient on this red curve. So curve fitting is the act of finding linear combinations of basis functions when you're doing this kind of empirical curve fitting and not mathematical subject matter derived models. So what does that give you in the end? Well, if you just multiplied each of these by a random number and added them up, we're just putting random betas on here. So if you put random betas, you got 4 random betas, multiplied them by these and added them up, you get things like this. So this would be the variety you would get if you got a set of betas and another random set of betas, and you got about 10 or 20 different random sets of regression coefficients. So instead of actually fitting data, we're just seeing what is the sort of universe of shapes that you might fit. And with 4 knots that are equally spaced, where the arrows are, you see that one of our fits is a rapid decline, and then it ends up going back up a little bit like a quadratic. Here's one that came down, it goes up, it goes back down. Here's one that stayed linear a very long time and it bended smoothly. And so that's with 4 knots. This is with 3 knots. When the join points are equally spaced, these are going to be symmetric. They're going to look kind of like a quadratic, which has to be symmetric around its vertex. So with 3 knots, it can go up and down, but not back up. 4 knots, it can go back up. More variety with 5 knots and more variety with 6 knots. Here's something that stayed linear a very long time, and then it made a sudden change. And you can just look at this to see all kinds of varieties. So if you think about what you see in empirical data, you very seldom see a relationship more complicated than one of these. The example is going to, the contrary example is going to be if this is time and you had a discontinuity because of an event. So the stock price took that sudden rise, sudden fall instantaneously when the CEO is indicted. So when this is timed, a lot of different things can happen. But other than time, you will very seldom see a true relationship in nature that's really more complicated than this. If you do have a relationship that has a sudden change, you can put knots closer together and it will capture that sort of change. So these are just examples of curve fitting, and to show you that if you didn't know any other way to fit nonlinear relationships other than regression splines, you would still be in good shape. So regression splines are really our go-to kind of easiest way to deal with nonlinearities in general. And they are direct competitors of things like nonparametric regression. and will do a very similar job as those non-parametric smoothers, and what's called smoothing splines, which are much more complicated than regression splines. But the fits will be very similar. So what we don't go into today is what I go into detail in the course is how do you write down the number of knots, and how do you select the knot locations. So the course notes has a lot of material about that you can look about later. Once you're all through fitting, you can rewrite the cubic spline back in the original spline format. Even though it has two redundant betas in it, you write down the equation as if they're not redundant, and that makes it have the simplest form. Instead of having differences in cubes everywhere, you've got it back to the regular cubes like we had before. So maybe we'll stop for a moment. Did anybody have any question about what spline functions are doing or why they work?
Have you raise your hands with any questions? And since we're taking the half mark section, you guys can ask questions as well for the previous parts if you have any. So we'll take, I saw Anand's question come up first. So you can go ahead with your question.
Yeah, sure. Professor, if you don't mind, can you please re-explain the concept of spline functions and what is the general purpose?
Yeah, so the purpose is to do curve fitting without assuming a linear relationship. And then the way I would describe them just in general terms is they're piecewise polynomials. So when you write it like this, you could also have a quadratic spline if you wanted to, but the cubic tends to work a little better. I would just say it's a regular polynomial. So that's a regular cubic polynomial. And then you have other cubic polynomials that are pieced together. So if you think about how you would draw a curve, and then you would connect it with another curve, and then you would connect it with another curve, that's what you're doing, like you would with a pencil. But you're making where the connections are, there is no vertical gap, and there is no slope change that you can see. There's nothing like this. It's going to be a smooth connection. So you're just piecing together cubic polynomials. I hope that helps.
All right, thank you so much. So then after
Yes.
that, we'll have Peter, then we'll have Burton, then Drew, and then you guys can go ahead. We'll take it from there.
Okay, thank you, Professor. I had a question about spline functions. So because they're so flexible and match most of the data sets very well, doesn't that also lend itself to a misrepresentation of the general trend? In other words, does being too specific to a given data set misrepresent the general trend that might be present in a, let's say, broader data set? And how do you solve for that?
Yeah, that's a super question also. And I would say that falls under the realm of overfitting. And overfitting is virtually equivalent to overinterpretation or fitting noise that doesn't replicate. And so I would generally call your phenomenon as overfitting. And so there is a contest between fitting well enough and not overfitting. You want to be just right. So underfitting would be forcing everything to be linear, and you'll underpredict. Your predictions won't vary enough. Underfitting would be omitting variables. So you could underfit by omitting variables, and then you could overfit by including too many variables or including too many knots. So a lot of what's in the course is straddling those two things and giving you advice for how to pre-specify the number of knots. And then what if your sample size did not support the number of variables overall? How would you deal with the case where your number of variables is too large for your sample size? So there's a lot of material in the notes that we don't have time for today that discusses the prevention of overfitting.
Thank you so much, Professor. My question is about like the spline functions, could it be a non-polynomial function?
Yeah, there's something called fractional polynomials, which are power logarithm type terms. So you could have terms like log of x, x times log of x squared times log of x times log of x squared. And you could put together these x by log sort of terms. That's called fractional polynomials. They don't work for negative x or 0x. So that's why I don't use them more, because you can't take the log of a 0 or a negative. And then there are, we'll see an example where we actually do a harmonic series. So we'll do a seasonal trend. So you do a seasonal trend usually with a harmonic series. And so there's lots of other things that are not splines.
Okay, thank you.
Good question again.
Thank you so much, Professor. So I had a question about the betas and how you're deriving them. So are you just using a lot of different betas to see what spline function would fit?
I would just word it slightly different, as we're specifying how many knots that we expect to be needed, or what's the maximum number our sample size will allow us to fit. And then we're fitting the function and using that to describe the relationship between x and y. So we're not playing with it over and over. We're trying to specify a single model, and then we're plotting from that model. I don't know if that gets at your question.
It does. Thank you.
All right, we can have Noah, Pandita, and Fayaz.
Thank you so much, Professor. I had just a very quick question, and this is something you touched on earlier. But what else besides the laws of physics might be considered like linear in our everyday lives, or is that the only application to that?
I can't think of many, actually. I used to think of one, and I found counterexamples. So what I used to think is, if you measured one variable at one time and then you measured it again at another time, that would be linear. So if you measured somebody's blood pressure at time 0 and then you measured their blood pressure 2 months later, that relationship, because it's really the same units of measurement, that relationship would by necessity be linear. And for blood pressure, it usually is kind of linear, but I've seen a lot of examples where you're measuring a health status here at baseline early, and then you're measuring it late, and it's very nonlinear. So even when it's the same variable measured at 2 different times, I see enough nonlinear relationships that are strongly nonlinear to make me think linearity is pretty much an accident that we don't see that often.
Awesome. Thank you so much.
Thank you, Professor. So my question is, how can we use splines to in our research work in different fields, like apart from just of one particular field? And like, what are the problems that can arise by using a spline?
I think it applies to every field in the world. So I think they're so general that it applies in medicine, economics, you name it. The problem with splines is, if you had like a very rapid change and you didn't put any knots there, you can undershoot that change and underfit. So you have to watch out if it's a very kind of complex or sharp change. And then your most common problem is you have to have a big enough sample size to be fitting the spline terms, because it's like adding more variables to the model. Almost like adding more variables to the model. You know, the more variables you model, the bigger your sample size needs to be for the model to work okay. So there is a little more risk of overfitting when you're not assuming linearity. And of course, if you assume linearity and it's not linear, you're underfitting. So you can get burned in either direction, but overfitting is one of our things to worry about with splines.
Thank you so much, Professor. My question kind of goes back to when we were dividing up the x-axis and the knots. I was just thinking, like, theoretically, would it be beneficial if we like divide up the x-axis into like an infinite amount of intervals so that like we don't have to take into account of creating like a whole new model because, you know, we forcefully make functions linear. And then kind of like a follow-up would be like, would this allow for just like using a single model rather than like using multiple models together, if that makes sense?
Yeah, I'm not sure about the multiple model question, but I think I can address the first part. The first part is exactly what a smoothing spline does. So a smoothing spline puts a knot at every distinct X value that occurred in the data. And then the problem there is if you had a sample size of 100 and you had no ties in the data, you're going to have 100 knots, and you'll not be able to estimate the coefficients. So you have to put a penalty function, and they tend to put a penalty function on the how wiggly the function is, like they do an integrated second derivative is your penalty function. And so you can't use standard estimation techniques, but you have to use penalized maximum likelihood estimation. So what you described is exactly smoothing splines, and they take specialized software and more computation time. The fit will not be enough different in my experience to be worth the trouble.
Okay, thank you.
I believe that is it with questions. Thank you so much, everyone. And we'll take questions again in a little bit.
These are super questions. So this is, let's see. Got to remember there was one graph I wanted to show. So when you think about how not to analyze data, there is an example back here that's like the horror story of data analysis. And this had, unfortunately, a lot of implications. So this is hemoglobin A1C. That's this big black line. That is a lab measurement that measures your average blood glucose over like 90-day period and it's used for diagnosing diabetes. And in this study, hemoglobin A1C is related to the incidence of diabetic retinopathy. So that's one of the really bad consequences of diabetes is your retinas can get very sick and you could go blind. And so what they did is they divided this into intervals because they didn't really know how to do continuous variable analysis. So there's a lot of optical illusions in this graph. So this is really poor statistical practice. You see the intervals are not equally spaced, but they're plotted as if they are equally spaced. So that's not an honest reporting of the data. And then it really causes a problem out here. So this last interval is open-ended. So this is where the hemoglobin A1C, which is also called glycosylated hemoglobin, is 6.2 or bigger. And so they just plotted of those in that group, what proportion of them had diabetic retinopathy, what percentage? And so that's a point out here. Now, this is not honest because let's suppose the range here is 6.2 to 10 and the average is 8. So if the average of those that had this was 8, you should be plotting this point way, way, way out here. And you see that that line is going to be way flatter. So what they've done is they interpreted for the world that they think that for diagnosing diabetes, you need a cut point of say 6.0 for hemoglobin A1C. And analyses like this were claimed to support such a cut point, and that's really bogus. So that's just an artifact of binning the data. So anytime you bin a continuous variable, you're asking for trouble. You'll get misinterpretation, you'll get an inefficient analysis. And then if you were to change the bins, you can change this figure arbitrarily. And we don't like things that are just totally arbitrary. So this is a kind of an example from hell in terms of bad statistical graphics and bad analysis simultaneously. So what would you do instead? Well, in a much bigger data set and a much better analysis, they used the restricted cubic spline function and a linear spline function to look at the hazard of getting diabetes in the future. So I like the blue curve better than I like the red, which is the linear spline. It's going to have elbows in it that we don't think are clinically reasonable. And you see that when you plot hemoglobin A1C versus the likelihood of developing diabetes in the future, there is no evidence of any sort of takeoff point here. So this is going from 4.8 all the way up. There's no evidence whatsoever for a threshold. If you were to predict the hazard of having a stroke in the future, there's no threshold. It's flatter, then it takes off. If you look at the hazard of having heart disease, not only is there no threshold, but it actually goes backwards. So you have what's called a hockey stick relationship. So you're showing evidence that it's not good to be very low on this scale. And then if you look at death from any cause, it's even more pronounced that having a very low value is appearing to be harmful to you. So if you were to use that the original analysis and you were to use a cutoff like at 6, not only is the cutoff not existing, there's nothing magic that happens at 6, but you would be losing, you would be calling all these people alike. You would be putting an average here less than 6. You'd be missing the fact that the fit is not monotonic. So you'd be giving the wrong answer everywhere except one point. So that would be what I would call negative information. It's not only not helpful, it's harmful because you would be not able to learn that it's a non-monotonic relationship. It's bad to be too low or to be too high. And then I think it's pretty convincing there's no such thing as a threshold. There's no point at which you could just say, are you less than that point or are you greater than that point? It matters how much less and it matters how much greater. So this is just showing that doing things in a way that loses information and is statistically inefficient is really problematic. So I've gone on record as saying this so many times, people are kind of sick of hearing it, but anytime you take a continuous variable and you bend that variable, you're making a mistake. So there's hardly any example where bending a continuous variable actually works as you want it to. The exception would be if you were to look at insurance coverage and you bend the data into age greater than 65 or age less than 65. Well, in the US, you get Medicare when you turn 65. And so that's a legal mandate. So bending it at age 65 or less is not going to be a horrible idea. Depends on your outcome variable. But in general, bending is a recipe for bad analysis and misleading conclusions. Okay, so that is our introduction to spline fitting, and then we get into some totally different subjects. Now this is a little bit in spline, but also complex curve fitting, just to show that you can do a lot more. And then how do you handle complex situations like interrupted time series analysis and seasonality? So this is looking at hospital admissions for acute coronary events in Sicily before and after a smoking ban went into effect in January 1st of 2005. And so the outcome variable is counts of, say, coronary disease cases. And then we do Poisson regression on these counts adjusted for the population size. And so we're going to fit that in a variety of ways. And this is using the RMS package in R. And so we're setting up our model and we're going to plot the raw data and we're going to plot various fitted values. And the first thing that we're going to do is the RCS is just an easy way to get a restricted cubic spline function. So that's a function in the RMS package. If you were using Stata, that's built into Stata. And various other packages have somewhat easy ways to fit spline functions. That's just a function that takes a vector and turns it into a matrix. So the matrix has those basis functions in the columns. So we're going to have a function of time with 6 default locations for the knots, because we're going to allow a complex time trend, because sometimes we see complex time trends. we're going to adjust for population size. This is a special thing you do with Poisson regression. And then we're going to plot the predictions from the model. And so you can see when you fit a trend in data, that trend makes you start to overinterpret things sometimes. And looking at the raw data, it's hard to see a whole lot of trend there. But this was a trend that was found by fitting the spline function. And then you have confidence bands for the predicted number of acute coronary cases per 100,000. So this is what a spline function fit looked like in our data set on these points, with knots put at 6 locations, default locations, according to the sample size in various regions of these points. Now, the next thing we're going to do is add seasonality to the model. And there's a beautiful website here that explains in some detail why this works. And the idea is if you're putting a cyclical trend in your model, you may not know that the trend actually begins on January 1st. It may begin on July 1st. It may begin March 13th. So when you don't know the starting point of the cyclical trend, the way you can make the starting point be a free variable is to add both sine and cosine terms. So the math just works out. So if you had your basis for fitting is a combination of a restricted cubic spline function and a sine and a cosine term, that's fitting a harmonic series with an unknown origin, unknown starting point for the cycles. But we're assuming the cycles are 1-year cycles. So we're assuming it's seasonal variation. And the way you make it a 1-year cycle is you have 2 pi divided by 12 because X is measured in months. And so now we have sine and cosine terms. So by estimating the coefficients of those, we're going to have a seasonal variation. In addition to this is our long-term variation. So once you know how to do splines and you know how to do a few other things, you can see how you can mix and match. So we're doing this as a transformation specified as this H function in the R language. And then when you fit that, you'll see that our long-term trend, it was averaging out the seasonal part. So now you see the long-term trend and you also see the seasonal variation and the estimation of the cycle start was around day 7. Month 7. So now we have a long-term trend added to a short-term trend. And this is a really nice way to think about doing time series analysis. This is the kind of time series analysis you would do if you weren't dealing with autocorrelation and certain other things. So the next thing we're going to do is adding more knots near the intervention point. So we want to see if there's any evidence that when the smoking ban went into effect, that something happened. So now we put knots, extra knots at 36 months, 37 months, and 38 months. So this is the point at which the smoking ban went into effect. We're not allowing for a regression discontinuity, but we're allowing for a sudden change in shape that's almost like a regression discontinuity. So you can see when you allowed for the shape to be complex in this region here, that it's almost on a vertical line, but not quite. So I actually like this better than using a regular discontinuity design and letting the data speak for themselves a little bit better. But you can see there's a little bit of evidence for something happening around the time of the smoking ban. Of course, there's so much variation from month to month that you can't have tremendous confidence in anything that you see. And then the last thing we're going to do is we're going to actually have a discontinuity. So we're going to have the long-term trend. I'm not writing RCS here just because I want to control where the knots are and do something a little bit differently. I have my seasonal variation terms, and then I have my jump. So the jump is an indicator variable about whether X is greater than or equal to 37. So that means you're at or after the smoking ban. And so by adding this indicator variable to the model, that's adding a discontinuity. So now we see our long-term trend, our seasonal variation, and we see a discontinuity, and you can compare that to the spline fit that did not allow a full discontinuity there. And you can ask whether allowing for a discontinuity makes the model significantly better than not allowing for discontinuity. That would be your formal test of the effect of the smoking ban. Although I would still take it with a lot of caution, because even though the smoking ban seemed to have a short-term effect, there's so much variation here, including coming back up here to the high range at month 60, that it's hard to have full faith in that. But this is to show you the sort of things you can do when you spend a little time specifying your model, and you can model short, long-term trends, discontinuities, anything that you want. That's just a different kind of example. All right. Now we go into a totally different subject. And the reason this one is here is there is a lot of misleading information out there, sort of like we have misleading information about COVID vaccines. We have a lot of misleading information about variable selection. So the bottom line is a lot of people get into a hurry, and they know that software has options in it for model selection or variable selection, and they get tempted to select those options in the software. This is really bad practice, but it is such an epidemic that it's hard to describe the damage that's been done by this way of analyzing data. So what I'm saying is people are using computers to tell them how to specify a model. And that's generally a very, very bad idea. It's just a sign of laziness because the computer just doesn't have the intelligence to do that well. But more to the point is the data do not have the intelligence enough to tell the computer how to do it. So the kind of information you find in the data is information about relationships and averages and things like that. The information in the data is too small to be able to tell you which variables are important. It's too hard of a job unless you have a million observations. Now, once you get to an enormous data set, you can do all kinds of things better, but the data in general do not have the information necessary to inform you which variables are important and which are more important than others. And that's true whether you're doing machine learning or you're doing regular statistical models. So this just goes into a lot of problems with variable selection. And one of the fundamental problems is it fails at exactly what it was designed to do. What it is it fails at selecting the right variables. And so you put in a lot of variables into a stepwise regression. Between 20% and 3/4 of the time, you'll select noise variables and fail to select half of the real important variables. So you're going to miss important variables. You're going to include noise variables. That's about the worst thing can happen for a method that's supposed to help you in selecting variables. That's sort of the kiss of death right there. If you have collinearity, it just gets much, much worse. The sample size doesn't help much, helps a little bit. And so here's a little simulation. And when you do simulations, you can learn so much. It's the only time we know the truth. So we can have a model that simulates some truth and find out if we can recover the truth without knowing it. That's your goal of simulation. So we're going to do what's called all possible subsets regression. And we're going to select the best model that maximizes the adjusted R squared. And we have a little simulation program. And the way we're going to simulate our data is we're going to have 8 covariates, 8 predictors that all have a random normal distribution with a mean 0 and a variance of 1. And they're all going to be uncorrelated. So there's no collinearity. So this is the easiest case to analyze. So these, you can see the ways these are generated, they're not collinear. And then what is the true relationship? The true model, this is the linear predictor, what we've called X beta. The true model has beta 1 equals to 1, beta 2 is equal to 1, beta 3 is equal to 0.5, beta 4, 5, and 6 are 0. Beta 7 is 0.4, beta 8 is 0. So that's our true model. So we want to be able to recover that model. These are the variables that should be selected, these 4. So we add some random noise to our dependent variable to get raw data. And then we run a variety of simulations and different sample sizes. So what happens? If you started with a sample size of 20, which is not very big, and you did 100 simulations, you find that on average 5.3 variables are selected, but they're not the right 5. So the number of times that the stepwise variable selection selected the right variables was 2 times out of 100 tries. So we did 100 simulated studies. It found the right model 2 times out of 100. Sample size 40, it found the right model 4 times out of 100. Sample size 150, 1 out of 5 studies, it found the right variables. Now remember, this is an easy task. This is 8 independent variables that are uncorrelated. We have a high signal to noise ratio. So we have a continuous outcome variable, and we have a somewhat strong model. That's a high signal to noise ratio situation. That's not like we see in human behavior and a lot of social science research where the signal to noise ratio is much lower. This is an easy problem, and it still didn't work. So sample size of 150, only 1/5 of the time it found the right model. Sample size 300, 1/4 of the time. You have to get up to a sample size of 2000, which is quite large for a high signal to noise ratio situation with 8 predictors, 8 candidate predictors. It still only found the right model half the time. That's pathetic. People are using this technique when you have 1,000 predictors. People are using this technique when you have 6 million predictors. So if you look at genetics research, it's very common to have 6 million genetic variants as independent variables. So if this procedure fails with 8 candidate variables, think about how it would fail with 6 million candidate variables that are correlated with each other. So this is bad news. And then there's another way to look at bad news, which is looking at variable importance. So if you can't say which variables are important and which are not, it's another way of saying, if you try to say how important a variable is, it's got a big margin of error to it. If you had a sample size of 1 million, the margin of error might be smaller, will be smaller. But we're talking about a situation where the order of importance of the predictors is not pre-specified. The researcher is interested in determining winners and losers. So what we can use is the bootstrap. And I don't know how many of you have been exposed to the bootstrap, but it's a very general purpose technique for simulating from your own data. So we can draw samples with replacement from our own data, repeat the analysis, and see if we get the same answer. And what we're doing over these repeats is we're ranking the importance of each predictor, and then we're getting confidence intervals on those ranks. This is something you don't see every day, but if people are trying to declare winners and losers, this is really necessary because it exposes the difficulty of the task. If you ran this for the 6 million genetic variant situation, you would find that you have no ability whatsoever to find the winning genes and the losing genes. Which genes explain a certain outcome? No ability. Now, when you're ranking the importance of variables, you have to decide the scale. You could rank them on the basis of a correlation coefficient, regression coefficient, T statistic, F statistic. I'm using a chi-square statistic. And the result, and this shows you the model I'm simulating from, these are the regression coefficients. So you can see that when I simulate data, I've taken total control of the situation. Beta 1 is 1, beta 2 is 2, all the way to beta 12 is 12. So X12 is the most important variable. X1 is the least important variable. And we have a random error term added to get our linear predictor, to get our Y realizations. And then we fit models that look like this. Ordinary least squares linear model, 1,000 repetitions. If you use R, this sort of programming is so easy to do because we're essentially saying rank the ANOVA of the fit. We're going to rank the chi-squares. And this is the bootstrap process that does that. Then the bottom line is here. X12 was supposed to be the most important variable, but in our sample, it came out the ninth weakest variable. So it came out as the fourth most important variable. X1 was supposed to be the least important, but in our sample, it came out as the second worst. The one that came out as the weakest variable was X3. That's wrong. But the confidence interval for how weak it is goes from 1 to 7. That's a 0.95 confidence interval. So roughly speaking, we're about 95% confident, which is not a right way to say it, statistically, that the importance of X3 is between the lowest and the 7th lowest importance of the 12 variables. The variable that came out the most important which was the wrong one, X9. The data are consistent with X9 being between the 8th weakest and the strongest. So that is our margin of error in estimating how important that variable is. So you can see that what stepwise regression is trying to do is to say that we can find clear losers and exclude them, and we can find clear winners and include them in our model. But this fully exposes the dilemma. So you're just not able to find clear winners and losers. It's just not that simple. So bootstrapping is a way to expose how something falls apart. Bootstrap is excelling at that. For whatever you're doing, you might be calculating a variance or a mean or a bias. The bootstrap is a great tool for exposing how something falls apart. It's unstable, it doesn't replicate. And that's exactly what we're seeing here. So we might stop and take questions here about stepwise regression topic.
Okay, so if you have any questions, please raise your hand and we'll take it from there. Okay, we have a couple of people. So we'll have Fayaz and then Noah again.
Thank you, Professor, for being here, first of all. I just want to, my question is, would you be able to go over like what noise variables are again?
What noise variables are? I'm just referring to variables that have a 0 coefficient. So we had, back in this other one, let's see. The way the data were generated, the true model is this. So X4, 5, and 6 are noise variables. X8 is a noise variable, just meaning they have no information about Y.
I understand. Thank you very much.
Yeah, so that if you select them, you're just selecting noise.
Okay, thank you.
Sure.
Hi, Professor. I just have another quick question. And I know you had a very, very strong warning and disapproval of using a computer to find your variables. I just had a quick question with that. In the examples that you're providing, examples of like why it wasn't a good method, as we increased n, did the computer find the variability, like the variable more accurately? I was a little confused on that.
Yeah, this is that's this point here. It does get better, but it doesn't get better fast enough. So this is one of those few cases where, you know, in most things, the sample size really works in our favor. Standard errors go to 0, things like that. This is not one of those cases. So that the situation gets better, that your chance of selecting wrong variables is going to go down, but it doesn't get low enough. And if you have a lot of collinearities in the data, the sample size will never help you very much.
All right, I just have, so if you, is there any possible value where you can increase it enough, or is it always kind of just playing a game of catch up with that?
It's more the game of catch up, but if you had uncorrelated variables, which would be kind of uncommon, then the sample size can catch up and ultimately you might be okay.
All right, thank you so much.
But we see correlations a little bit too often.
All right, cool. Thank you.
All right, are there any other questions? There's no other questions, Professor, so
All right, good.
go forward.
So what we're going to do now is something really different, and I don't know how many of you have studied the binary logistic regression model. This is one of the most common models, and that's for use when your outcome is a binary variable. We had some bad news this week where one of the greatest statisticians that ever lived, D.R. Cox, died in England. He was Sir David Cox, and he had a famous 1972 paper where he developed what's called the Cox model, which is used in survival analysis. And in 1958, he developed the logistic regression models. He's famous for two of the most commonly used models in all of statistics, plus a lot of mathematical stuff. I think his 1972 paper had more than 56,000 citations to it. And so the good news is he lived to be 97 and he was still lecturing up to like last year. So he had an amazing life. So we're going to use his binary logistic regression model because what we're going to do is to predict the probability of something instead of predicting a mean. And so this is a probability model. And I think what's interesting about this case study is that most of the time in what you'll encounter is you'll be in a predictive mode. You're trying to predict what's going to happen in the future. This is an autopsy mode. So we're trying to predict, we're trying to decode what did happen in the past. So when the Titanic hit the iceberg in, I forget, was it 1914, something in that range? When it hit the iceberg and went down, they say women and children first are supposed to get in the lifeboats. Is that really what happened? So we're doing a retrospective analysis, and anytime you get an opportunity to do a retrospective analysis to find out what really happened in a certain event, it's fascinating. And there's a lot of examples of that kind of analysis looking backwards. One of the kinds of examples that's interesting is you can record what decisions people made and then record what they had available to them when they made the decision. And you can backsolve for what cues they used in making the decision. That's a very interesting use of logistic regression again. So there's a lot of resources about the passengers on the Titanic. And we're going to ask the question, were women and children first? And by asking that also, we want to know, what did a child mean to the people making the decision? If you were assigned to a lifeboat, what was there an age cutoff for a child? What did they take to mean by that? So if you look in the data set we have used here, this is a data set of 1,300 out of 1,500 passengers. And we have passengers in first, second, or third class, depending on how much money they were willing to pay for a ticket. The third class passengers were kind of deep in the ship, didn't have a view. First class passengers are up high and they had the best view of the ocean. 38% of the passengers survived. The age range was from 2 months, so we had a baby on board, all the way to 80 years. This is the distribution of age. And this is a good advertisement for a spike histogram. It's just a histogram showing you the full resolution of the data, which I like better than the traditional histogram. There were 2-to-1 males to females on the ship, and this is really bizarre. Why should that be so unequal? But the reason is women were not allowed to travel alone in the early 1900s, and men were. So you could have a lot of men by themselves on the ship, unaccompanied, but the not unaccompanied females. So that means the numbers are going to be less here. You had the number of siblings or spouses on board with the passenger, the number of parents or children with the passenger. And we're not going to really be analyzing those, but this is a number one example besides that diabetes example of why you never bend a continuous variable. This is bending age by default bends. These are quartiles. So this is the first fourth of the data was 290 passengers. The second quarter of the data was 246. There were some ties in the ages and so on. And the only action we see is that those for whom age was missing had a lower chance of survival. They had a lower chance of getting on a lifeboat. If you look at those for whom age was measured, there's no pattern here. And an interesting thing happened with this exact data set was used in a Kaggle competition. That's a machine learning competition. And the year the data set was used, IBM Watson won the contest, and everything they did was wrong. Every single part of their analysis was wrong because they end up bending the age variable and not analyzing it correctly. And so when you bend the age variable, you see nothing because all the action is right in here. All the action is between 0 and 22 years. So you've masked all the action by lumping these and pretending they're a homogeneous group, and they're not homogeneous. So this whole thing is misleading. Now, for female and male, you see a huge difference in getting a lifeboat, huge difference for first, second, third class. And then the next thing we're going to do, this is a useful thing to do when you have a binary outcome. You can use a non-parametric smoother to estimate smooth proportions. It's kind of like a moving average, but it's a moving slope and intercept. This method is called low S, I believe. If you were to relate age to the proportion getting on a lifeboat, you see this kind of relationship, and that relationship is utterly meaningless. So when you're doing data analysis, a lot of people say, give me the descriptive statistics. Well, this is a complete waste of everybody's time because it doesn't make any sense to look at age without looking at sex and passenger class. So that's called confounding. Likewise, if you don't look at passenger class, but you just look at sex and age, you get this bizarre relationship that the females, the older they are, the more likely they were to get on the lifeboat. So that makes no sense at all. The males make sense. The young males had some chance of getting a lifeboat, but once a male hit 21, he's on his own. His chance of getting saved is very low. And I think the water temperature was low enough that the survival time in the water was less than 2 minutes. You know, once you're in the water there, in the North Atlantic, you're gone. So this is residual confounding due to passenger class. This is an example of presenting marginal statistics that are meaningless. And we see papers, journals wanting you to waste time presenting these. It's a complete waste of space and time. When you stratify by passenger class, you see these relationships. This is not helpful because you're not accounting for the sex of the passenger. Now, when you cross-classify on passenger class and sex, you start to see a real story. So these are the first class females. They had almost 100% chance of getting a lifeboat. There were just a few here that were a little younger that didn't get on a lifeboat. A little worrisome there, but they're way up against one here. That's good for them. Now, what about the second class females? Okay, the infants got on the lifeboat. The teenagers almost did. And then once you got older, it just got lower and lower. The third class females are here. So when they say women first, they don't really mean that. If you're first or second class woman, yes, you're first. But they didn't really hold lifeboats for the third class women. The third class women, for much of the age span, have the same chance of getting a lifeboat as the first class men. And then you have second class men and third class men, they're in big trouble. The kids, you know, the kids had some chance of getting in a lifeboat if they were male, but these are hopeless. So second and third class men didn't matter a whole lot there. And so based on that, you would say, what did they mean by a child when they said women and children first? Well, you can see now. They didn't really define what a child meant, but they really defined what an adult meant. So an adult meant 21 or older, basically. And then the closer you were to infancy, the more chance you had to get on a lifeboat. So when you go and do the formula analysis, which is pretty involved, and I'm just going to give you a highlight of it, what we're going to do here is to fit a model. This is a logistic regression model using the RMS package in R. We're predicting the probability of surviving, which is the same as getting on a lifeboat. And we're going to have a main effect for sex, a main effect for passenger class, a restricted cubic spline in age with 5 knots. And this notation here, which looks like to the second power, and this parenthesis, this doesn't mean to square things. This means to include all two-way interactions. That's just a shortcut in R. So that's the main part of our model is we've got the effect of sex, passenger class, and age. Age is not assuming linearity. We're allowing for all two-way interactions. And when you go through that, you can see strong evidence that something's associated with being selected for a lifeboat. The generalized R squared is 0.55, which is very high. So to get a high R squared for a binary outcome is very difficult. And this is the C index, or area under an ROC curve, is very high. So the survival patterns in the Titanic are very easy to see. You have strong relationships, very predictable outcomes for the most part. The model is going to be having a lot of spline terms in it, a lot of interactions. You're not going to profit from looking at those coefficients. But when you make predictions, you'll see predictions and confidence bands. This is our predicted survival as a function of age for first class females and first class males, second class females, second class males, third class females, third class males. You compare this to the non-parametric, which is like moving proportions. You'll see a really excellent agreement. So the logistic model is mimicking what we did with the non-parametric moving averages of proportions. There's a lot more to this and interpretation, and there's a lot of stuff related to model validation and dealing with missing ages that we don't have time to get into here, but you might look at that in the future. So it's a pretty long case study, and it goes into detail about dealing with missing data, a lot of other complexities, but I wanted to give you just the main look of the predicted values to see that you can learn a lot. And the goal, where IBM Watson got it terribly wrong, is they stated the problem as a classification problem. They stated it as, we want to classify who lived and who died. That is of no interest whatsoever. We don't need to classify people as dead or alive. The interest is completely in analyzing tendencies. So analyzing tendencies means what is the probability of death as a function of the passenger characteristics. We want to know what is the tendency to be selected for a lifeboat if you were 18 years old versus 40-year-old, male versus female, and so on. So the whole interest here is the analysis of tendencies to be selected. Our analysis, we have no interest in classifying people as selected for lifeboat, yes or no. So that's a classification problem that is irrelevant here, and IBM could not have been more wrong in their machine learning application. So I want to close it with just a couple of graphs. This is what it looks like when you have a regression model with a lot of spline terms in it, and you want to show the partial effect of every variable in the model. The variable here is the log of the number of days that somebody survived after they entered the intensive care unit and they were very sick. So these are critically ill patients. The log of how long they lived is our dependent variable. And we have the contribution of various variables. The age relationship is fairly linear, and the importance of age is medium. This is serum creatinine, which is your kidney function. This is the chi-square for testing whether this curve is flat or not. The kidney function is all important when you're in the intensive care unit. When your kidneys shut down, you expect bad things to happen. A little bit of nonlinearity here. You have this being very non-monotonic, highly nonlinear. Mean blood pressure versus outcome is very nonlinear and very non-flat. Lung function is very nonlinear versus outcome. So these are called partial effect plots, and you can see how nonlinear things came out, how important they are, which is basically also how steep these relationships are. And then you can put it all together. You can look at a ANOVA table about the importance of various things in your model. You can see that kidney function was one of the most important variables, but the disease you had is even more important. And then you can put this together in a chart that shows the ranking of the importance of the variables. You should use the bootstrap to put confidence intervals on that to be thorough. These are effect ratios. What's the effect of each variable varying at one at a time? If you had to select just one interval for varying it over, like the age varies from 48 to 74, which is the interquartile range, that lowers your survival time by a factor of 2. And then you can have a graph of the whole model. So the point about a nomogram, in R, this is one command. The point about having a nomogram is it helps understand the model, and it helps show you that no matter how many variables you have up to a point, and no matter how nonlinear the variable is, it's still an easy thing to handle in terms of how you get predictions and how you interpret the model. So you can see the serum creatinine effect wraps around the axis. That had a U-shaped effect, you'll remember from the plot. Age was kind of linear. You see a sort of linear equal space tick marks until the end. Heart rate, kind of linear. So you have all of these variables here. Mean blood pressure was very nonlinear. What disease did you have? You can translate all these things to points, and you can add up those points and look at your total points and look at your linear predictor, your median survival time, and your mean survival time. So the nomogram is an educational tool that really helps you understand the shapes of the relationship, the strength of the relationship, which is how stretched the axis is. And you can also get predicted values from it, especially if these variables do not interact. So that is what I'll close with, and we can see what sort of questions remain.
All right. Professor Harrell, if you are open to any questions right now, we have a person raising their hand. I'm not trying to pin them.
Good.
Thank you, Professor, for the great lecture. I just have one question which is not exactly related to understanding any model, but just in general. At this point, should we be just trying to understand the models and not care much about how you like program the model in R to perform the analysis, or is that something which we should also look to learn, or like for like right now?
Yeah, that's actually a question that's more difficult than it seems, because this relates to what you'll be doing in the future. Do you want to be self-sufficient, or do you want to be part of a team? So in my career, I've always been part of a team, and it's usually a team of doctors and statisticians and epidemiologists. Sometimes there'll be a health economist involved in the team. And so we found division of labor gives you the most efficient research. Other people find that they're put into a job where there's not a colleague who knows a certain skill who you can work with, and you have to learn it on your own. So it's just a general comment that you have to sort of predict what setting you're going to be in to know how self-sufficient you can be. And I think the way that I try to teach things is we have a lot of resources teaching people what mistakes not to make, because that's the thing you can learn first. It's harder to learn how to do everything right. It's easy to learn what not to do. So I tend to teach people what not to do first, because then they will not make a big mistake, and then they can spend their time trying to make it good. I don't know if that helps.
Yeah, that made a lot of sense.
If there are any questions about your project, you can also go ahead and ask them. We won't be having office hours today. So all right, Peter, you can go ahead.
So this is just in addition to my previous question. Are there any signs that you've either under predicted or over predicted when it comes to creating a spline function?
Of course, if it all depends on whether you had previous subject matter. So if somebody did an experiment that's using data similar to what you're using, and they wrote it in a journal article, and you can read the article, you may see some graphs that give you a start on how to model it yourself. But if you don't have any outside knowledge already available, it's a tougher question. But there are some indirect signs. So we have various ways that are detailed in the book and the course notes for quantifying how much overfitting you have in your whole model. So one of the really cool ways to do it is you measure how predictive your model is in comparison to how hard you had to work to make the model. So there's a simple formula. If you put your model's value in a chi-square scale, which is called your model likelihood ratio chi-square statistic, you can take your chi-squared minus p over chi-squared, where p is the number of parameters it required. P will be larger if you have a lot of knots in the spline function. So chi-squared minus p over p actually measures the amount of overfitting, and it gives you an idea whether you've overdone it for how much information is in your sample. So I would look at, this is called the heuristic shrinkage estimator. So you might look that up in the notes, the heuristic shrinkage estimator. The bootstrap can also give you the same information with just more time required. There's another measure called AIC, which can play a role in this context.
All right, if there are any more last minute questions, you can go ahead. If not, I'm gonna go ahead. Professor Harrell, thank you so much for lecturing for us. Would you like to give us your contact information in case any of the students or any of the fellows would have any way of reaching you for any questions during the project?
Yeah, the best way to do it is if you have a very general question, like about spline functions in general, that would go here to stats.psychexchange.com. If you have, which I often answer questions on that site. And then if you have questions that are more specific to what we talked about today, like specific examples or specific philosophies that we talked about today, that is best done here. So you click here and it will navigate you to various other subpages depending on what chapter of the book you're asking about or what's the topic. So today we talked a lot about chapter 2 and a couple of later chapters. And so this would be for more a little more specific to what we talked about today. This is for general. This one I monitor more closely since I'm the moderator of that site.
All right, thank you so much. If any of the fellows have any specific questions for the TAs, you can go ahead and ask them now.
I just want to quickly ask, in the beginning of this of today, you guys showed like a stacked workplace, and if you want, we want to join or not. Is there a link for it?
I think they'll be sending that out in an email later today.
All right. Thank you very much.
Yeah. All right, if that's all, you guys feel free to leave. Have a good rest of your day or night.
Thank you.
Thank you.
Thank you.
Thank you for your
Thank you,
time.
Professor Harrell.
Thank you. Thank
You're
you for
welcome. And
your-
everybody stay healthy, please.
You as well. Thank you.
Thanks.
Thank you.
Thank you.
There was something I wanted to ask the DA actually. I sent an email regarding this also, but I was not able to attend the first part of today's meeting due to another commitment, and I missed like basically the part before the lecture started. So could someone just give me a rundown of what happened there, like, very quickly?
So what we did, basically we just did like a couple of icebreakers, and then we just met with our groups. I don't think you missed too much. We didn't get too much started or anything, so you should be fine. Just make sure you can attend like starting next week.
Yeah. And another thing, I forgot to attach my like Word document to one of the Edmodo assignments. I've attached it and resubmitted it now. Will it affect my course grade?
It should be fine. We will take a look at it. I don't know if it's going to affect it or not, but we'll take a look at it today.
Thanks a lot.
Thank you. All right. Ryan asked me to, one second, I'm trying to go back up. Ryan asked me to starting the debrief if he's not back. Just if there are any people here that are still. All right, I think that's only the, yep, all right. So what did you guys do in your waiting rooms? I think that's all we have to go through today. So we can just start off whenever.
Okay, my group, we exchanged contact info. And we basically started listing out everything we wanted to include in our background.
My group did the same thing. We introduced ourselves to each other, and then we put all the information from the homework onto a doc. And then we started like brainstorming on the background. Like one concern I guess my group had was like communication. They wanted to use Slack, but I wasn't sure like if you guys were gonna make a Slack channel for us or like if we would have to make our own separate ones.
I believe the Slack channel is going to be made by us. So, yeah. If you guys, I know for my group, we're using like a different separate like Discord server for like just our group to communicate with each other. So if you guys want to do that as well, like just between your own group,